Consider this example of 100 factorial. It can be computed using 99 multiplications, or 99 additions if you use logarithms. In the last lesson, we developed an approximation to the factorial that can be computed in far fewer mathematical operations. Today we are going to develop a similar approximation that is more accurate. Commonly, it is known as Stirling's approximation. You can see that this only involves a few mathematical operations, far less than 99. Of course, root extraction via Newton's method can require several iterations. If approached the right way, 36.7879 to the 100 can be computed with 8 multiplications. This was covered in another lesson. In the end, our final answer is in the bottom line. Not exact, but a lot closer than the previous approximation we used, and a whole lot faster than 99 multiplications. To understand where Stirling's approximation comes from, we must begin by defining this integral as a function of n. Don't worry just yet why I'm bringing this up. It should make more sense after a few minutes. If you are curious for more information, research the gamma function. It is closely related to this integral. Here are examples for the first few integers. F of 0 is simply the integral of e to the minus x. F of 4 is x to the 4th times e to the minus x. It should be noted that these integrals are all equal to some number. In a short while, we will see how these numbers are obtained. In order to integrate the function just seen, we must employ integration by parts. That is boxed in orange. A simple derivation is provided above it. Pause the video if you are curious to understand why integration by parts works. We choose u equal to x to the n. dv is e to the minus x dx. Everything else we just plug into the form. That leaves us with the last line. Now we must evaluate that integral at the lower and upper endpoints, 0 and infinity. The first term disappears. Part of the second term I have underlined in blue. Notice that that is simply equal to f of n minus 1. So f of n equals n times f of n minus 1. This is called a reduction formula. It is easy to verify that the integral of e to the minus x from 0 to infinity equals 1. So we define f of 0 is 1. Next we use the recursive definition to get f of 1, then f of 2, and so on. But wait a minute, we already know another function that is recursively defined the same way. It is the factorial. N factorial is simply n times the quantity n minus 1 factorial. Start by defining 0 factorial as 1. The rest follows accordingly. Putting all that together, we can say that n factorial is equal to the integral of x to the n times e to the minus x from 0 to infinity. That is boxed in red. Now let's look at the integrand, x to the n times e to the minus x. Take the natural log of both sides. Using laws of logarithms, we get n natural log of x minus x. Now we are going to substitute x equals n plus z. Why? It'll make more sense at the end. We must manipulate a few things and then substitute back to the original form. Just bear with me for now. Some algebra and laws of logarithms split this up from 2 terms into 3. I've underlined the middle one in purple. We are going to rewrite that in a different form. Observe the series expansion for the natural log of 1 plus u. That is boxed in orange at the bottom of the screen. Above it is a simple derivation from the geometric series. Pause the video if you care to follow through the details on your own. Using that series expansion, we are going to rewrite the term underlined in purple. I have truncated after z squared and eliminated all the higher order terms. On the next page, we will substitute the result in the last line. So we substitute that for the middle term. Notice in the second line that the z's cancel each other out. Our final result is in the last line. Our next step is to exponentiate both sides. Some more algebra gives us the final result. I've underlined in green e to the minus z squared over 2n. This is still the integrand, so to get it back to the original form, we must integrate it. In order to do that, we must adjust our limits of integration accordingly. The lower limit was 0 for the variable x. It becomes negative n for the variable z. That is seen in red. Notice that I can factor out front n over e, quantity to the n. Why? Because it doesn't contain the variable z, for which we are integrating. The green part stays inside. It is a function of z. Stirling's approximation works well for large n. So for now, let's just pretend we can make the lower limit negative infinity instead of negative n. That is seen in blue. Soon we will see this distinction can be justified. From statistics, this function looks awfully similar to the normal distribution. The area beneath the bell curve can be calculated. We can explore this more thoroughly some other time, but that integral equals the square root of 2 pi m. Thus, we are able to evaluate the integral seen at the very beginning of this lesson. The final approximation is boxed in red. That is effectively Stirling's approximation to the factorial. Graphically, this is the bell curve we want to integrate. Y equals e to the minus x squared over 2. We want to find the area in red. But what if we don't want to integrate from minus infinity to positive infinity? Here I have summarized a couple results. I used numerical integration techniques to evaluate the integrals. Notice there's a small change when the limit is 4 instead of 3, 2.506 instead of 2.499. That value matches the square root of 2 pi up to 4 digits. This effectively means that our derivation of Stirling's approximation will give a good answer for any number n larger than 4. After that, the difference becomes negligible. Now to summarize, our first approximation to the factorial, derived in the last lesson, tends to overestimate. It is an upper bound. Stirling's approximation tends to underestimate. It is a lower bound. The true value of the factorial is somewhere between those two. In the last line, I show the ratio of the square root of 2 pi over e. It is approximately 0.92. We saw that in the last lesson. Now time for a table of data. See how the Stirling approximation is always a bit lower than the true factorial? It is accurate to within 1%, which is much better than last time. Also, the larger n becomes, the more accurate is Stirling's approximation. This is a side-by-side comparison of last lesson's approximation to the Stirling approximation. Notice that one tends to overestimate, while the other tends to underestimate. After n equals 2, Stirling's approximation is always closer to the true value of the factorial. So if your calculator doesn't have a built-in function for the factorial, this is a quick way to estimate it, especially if n is large. You will save yourself a lot of time over repeated multiplications. What do you think of all this? Let us know in the comment section below. I appreciate your support and look forward to seeing you again.